Okay. The second item of this week is technical progress. So remember last week I mentioned that Thomas Malthus worried that when population grows too rapidly, then because of diminishing marginal productivity, the labor productivity will decrease. But that was not the case because the cross derivative of labor with respect to capital increases. So now that cross derivative positive often associated with technical progress. So let's say we want to model that technical progress. First of all, look at this production function. So apart from the function of K and L, capital and labor, we also have a factor A, which accounts for every other things that influences the output quantity apart from K and L. And this factor often evolved or changes over time. So for that reason we write it as a function of time t. So A is a function of time and usually it is increasing. And that is the technical progress factor that we wanted to model. However, let's first look at the graph, how to express it graphically. So imagine in the beginning, like in the history, originally we need this amount L0 of labor and this amount K0 of capital to produce a certain output quantity Q0. Now, and because of technical progress, let's say we need less labor to produce the same quantity of output. Well, in general, we could think we also need less capital, but like for now, let's stick to that case. So now we only need, for example, L1 to produce the same Q0. How to express that? So Y capital remain the same as before now. We could use another isoquant. Here's not so now what I'm drawing, but yeah, let's bear with it. So this is another isoquant. However, important to note that this isoquant, let's call Q prime 0, represent the same level of output as before, as Q0. Yeah? So in this case, the shift toward the origin of the isoquant map doesn't mean a lower input level. Just remember that, just say that, okay, now we need L1 smaller than L0 for same Q0. So here you could, okay, easily come to the conclusion. So the impact of technical progress is enough. Let's take the output divided by L1 minus the output divided by L0, right? Output stay the same. Labor decreases, like average productivity increases. However, there's one danger there, because now let's, for example, if you reduce labor to L1, but you increases K to K1, this level, then you will also end up in the same output level, no? Q0. However, this is just a change in the combination of input without any technical progress. But still, the effect on average productivity can be written exactly the same. So how to distinguish these two cases? That's where we need something called growth accounting. So it says that the growth in output will equal the growth in technical progress plus the elasticity of output with respect to capital times the growth of capital, and similar for labor. With here we define the growth rate as the change over time of a variable, let's say x, over time, so it's derivative with respect to time, the time variable t, and then divided by the total amount of x. So that's the growth rate in percentage per unit of time, for example, per year, per month, per century. So now we will see how we arrived in this, and also how do we use it to calculate technical progress, and so and to distinguish the two cases. But first, let me write down here. So because here we have the growth rate of K and L, so that means we also can accept or can assume the case that K and L is also growing over time. So for that reason, we could write it as, here, let's put it here, a different color maybe, Q as the function of AT, and times the function, some function F of capital and labor, but now KT, LT, because can also change over time. Before we start, let's do something simple over here. So the first thing, if Q equals A times F, then you also have A equals Q over F, right? And the second thing, similarly, you also have F equals Q over A. We will need it later. Okay, so now let's differentiate this production function with respect to t to see what happens when it changes over t. So differentiating with respect to t. Now differentiating q, let's say q. Okay. We would have dq over dt on the left hand side, and now to the right hand side we have, because here is a product of two functions, right? The first function at, the second function is the function f of some other functions of t. So now let's do it step by step. We first need the product rule. So the derivative of the first function a with respect to t times the second function, which is f kt lt, plus the first function itself at times the derivative of the second function. So this is d of f kt lt with respect to, right? Let's write it here. So this is product rule. Now, for the second step, let's rewrite it dq, over dt equals dA over dt times f. Now I skip the part in the bracket, but you ultimately understand what is there, no? Plus, okay, how how to take the derivative of this f with respect to t. Because f is the function of k and l, and k and l is in turn the function of t, so that we need the chain rule. But now for two variables, k and l. Now, so the first thing is we take the derivative, the partial derivative of f with respect to, still remember partial derivative rule chain rule, with respect to k, right? Times the derivative of k itself with respect to t. And do similar for later. So df over dl times dl over dt. Now, and this is chain rule for two variables. Okay. The next thing we should do is, because of this growth rate, and we wanted to have growth rate of output on one side. So now we have dq over dt. We will need q itself. So we need to divide both sides by q. Okay, here now things get a little bit complicated, but let's do it slowly. So we divide both sides by q. On the left hand side we will have dq over dt divided by q, right? And on the right hand side, now let's take it step by step. You have dA over dt times f. Here I use the first thing here, f equal q over a. So that is q over a, and then divided by q, right? Don't forget that. Okay, that's the first thing. The second thing, we distribute everything else in the bracket out, but at the same time divided by q. And here I need the second thing, the a. So I will exchange the a by q over f and takes everything but divided by q. So 1 over q, let's write it there, times df over dk times dk over dt. Now, and then plus, again we have q over f, this thing, times 1 over q divided by q, times partial derivative of f with respect to L times the derivative of L with respect to t. Okay. Now, this is like already in shapes. I will show you, but before that, let me also jump one step ahead, times k over k. And here you times L over L. Basically that means times 1, but we need this. And why we need this, you will see in a second. Okay. Now, on the left hand side, you already have like exactly by the definition of growth. So that's, but now the x is replaced by q. So that's the growth in output q, right? It's derivative with respect to time, then divided by itself. Next thing here, we have q on numerator, q in the denominator, so it's gone. And what you have left is dA with respect to t over A. So that's the growth rate of A. Now, very good. Now take it slowly over here. Okay, so again you have Q, cancel out. And then you have the derivative of F with respect to K times K over F. What is that? That is the elasticity of Q with of F. Let's stick to F first. With respect to K, right? Times what's left? The thing left is we have dk over dt, and then everything divided by t is here, with k replacing x. So that's actually the growth rate of k, right? Plus the next thing, also cancel q, and then you have partial derivative of f with respect to L times L over f. So this is the elasticity of f with respect to L, right? Times, again you have the L over dt and then divided by L, so that's the growth rate of labor. Now, so it's almost the same. Okay, now the remaining question is, why do we have the the elasticity of F with respect to K? What is that? So if you take the derivative of Q with respect to K over Q, then you have A, because here's A without K, so the derivative A, writing again, dF, right, over dk over Q. So you have, if you have like the elasticity of Q with respect to K equals this term, K over Q over Q. Q here is 8 times F, right? And then times K, right? So at the end, A cancel out, and it's also equals to the the elasticity of F with respect to K. So for that reason, now we could write it already that Q equals GA plus the elasticity now of output Q, K replacing F by Q because here's equivalent now, times GK plus the elasticity of Q with respect to L times GL. So that says the growth of output over a certain period over time on average will be the sum of 3 different factors. The growth of technical progress, then the growth of capital times the elasticity of output with respect to capital. How output changes when capital changes, right? Percentage term, of course. And then plus the same thing, elasticity of output with respect to labor times the labor growth, the change over time of labor. And we could already distinguish the two cases here, like I said in the beginning, because the case where L changed from L0 to L1, but K changes from K0 to K1 should be accounted or should be controlled in the two later terms already over here. And the residual of the growth after taking care of the changes in labor and capitals should be attributed to technical progress. That's how we go about that. So let's do an example, numerical example. So this is a study of Solow, quite famous. I think you will encounter such models if later you take development economics or so. So here, let's say in the US, in the period from 1909 until 1949, the average growth in outputs measured was 2.75% per year. Everything measured per year. And the growth in labor is 1% per year. Growth in capital, 1.75% per year. And we also have the elasticity of output with respect to capital and labor already. So now we just need to calculate the technical progress. So you have everything you need on the right hand side, and we also have the number for the left hand side. So for that we will write GA equals GQ minus elasticity of Q with respect to K times GK for capital. Oops. Not plus here, but should also be minus, because now we put everything to the left hand side. Minus elastic Q with respect to L times GL, right? And now we have every number just plugged in. So GA equals 2.75 minus elasticity of output with respect to capital here, 0.35 times the growth of capital, 1.75, right? Minus, again for labor, so the elasticity of labor of output with respect to labor is 0.65 times 1%, right? Then, if here you have 0.65, the result here 275, so that is 2.1 left, right? And minus here 0.35 times 1.75 is 0.6. So at the end it equals 1.5 GA% per year, right? So in this 2.75% of output growth per year within this period of time in the US, the technical progress accounted for more than a half of that. That's how we think about it, apart from the changes in labor and capital.